Check it out now, y'all.
nanoHUB-U, online instruction.
Hi everybody, welcome back to nanoHUB-U, and this will be lecture 2.3, and we'll explore some of the properties of S-Matrices in more detail today. So basically what we're going to ask is the following: what happens if we have a periodic wave optic system? Okay, and so we can kind of think that there are actually two different types of coupling that we can care about here. And so one kind of coupling would be a layer-to-layer coupling. And then that should give us kind of refractive behavior. But then there can also be a mode-to-mode coupling, which may be between modes that have different propagation vectors parallel to the interface. So we can kind of consider that to be a diffractive coupling. And then we want to really see if we want, like, kind of treat the most general case in which both are possible, can we do that in a single framework? Okay, so that's very important because, like, right now we're basically only doing the first one, but we haven't treated the second. So what are we going to do? Basically, we want to divide the structure into layers like we did before. And then we want to find now block states in each layer if each layer is periodic. And that means in the direction that's perpendicular to the surface. Okay. And then we want to calculate a transfer function for the field amplitudes between the different layers. And then, much like we did before in the purely refractive case, we want to develop an S-matrix that includes diffraction now. And then, of course, like, once we have that S-matrix, then it should be pretty easy to choose the inputs from both sides and then get the outputs that result, both the transmission, reflection, and losses. So fortunately for us, this has already been done in a pair of research papers, first by Whitaker and Kulshaw in PhysRev-B in 1999, and then there was another one by Tekodiv in PhysRev-B following up a few years later in 2002, and since then there's been other work as well on that topic. So basically the strategy is the following, which is to do a Fourier series expansion in each layer of the periodic H fields. And so, in other words, what we're going to write down is a product of H fields, like, that are polarized in both the X direction primarily, as well as those that are primarily in the Y direction. And those are going to be designed so that the overall divergence of the H field vanishes, which satisfies one of Maxwell's equations. And so, of course, it depends on the K and G vectors, like exactly what value is needed in order to get zero divergence. But in general, I can assure you that the solution would look something like this form, where we have this, basically the function that's polarized in the X direction, which has a component in the Z direction as well to cancel out the divergence, and then something similar in the Y direction. And then we can actually rewrite that in the momentum space, the reciprocal space, as kind of a sum of those three terms, basically kind of bring those two things together, and then dropping, like, the real space representation. And of course, because of Maxwell's equations, we can also use that H field form to directly derive the E field. And then it becomes obviously a little more complicated, but it's effectively motivated by that same formulation you saw for the H field. And so now you have, like, both the H field and the E field in kind of the momentum space as a function of position. And so it's kind of a mixed representation in the sense that we only keep the Z dependence, but there's no X and Y dependence anymore directly. And so we can actually now combine those two E and H fields and combine that with the wave optics equation, which is kind of like a Helmholtz equation, in order to write the overall kind of linear algebra problem that's associated with this system, like both in terms of these x polarized terms and then the y polarized terms. And so then this is actually going to be true whether we're talking about like a E field or H field. And so we just write kind of the state vectors as phi x and phi y, although it's probably easiest to derive these expressions by starting off with the master equation for the H field, which, as you probably remember, is the curl of epsilon inverse times the curl of H is equal to omega over c squared times H. And so then once you incorporate this sort of formalism of the basically representing the H fields, then it becomes a slightly more complicated set of terms, which we write as like kind of this product of this eta vectors or matrices, which we can represent kind of more compactly as H, and then these K matrices, which we represent as capital K. And so then we write this kind of in a compact notation as H times Q squared times, of course, the identity matrix plus K, and then plus kind of what we call a script K, which is kind of a composition of the K matrices and the eta matrices. And then that's set equal to omega squared times phi. And so now we have an eigenvalue equation. Of course, this eigenvalue equation is not symmetric anymore. And we have actually a unique orthonormality condition in order to enforce the relationship between the eigenvectors. And so it looks something like this, where actually between each eigenvector and there's basically this omega squared minus script K matrix that's kind of imposed between them in order to get kind of a Kronecker delta type relationship. So then, in other words, that means that whenever you enforce that condition between phi n's, you don't just multiply phi n transpose times phi n prime, but you multiply that thing in the middle. Okay, so why are we interested in doing that? Obviously, it's more complicated, but it does have some big advantages. The biggest advantage, of course, is that we're not forced to make any real assumptions about our structures other than they could be represented as periodic structures. But we're effectively able to not just do 1D layer structures, but also 2D and even 3D layer structures without any problem. So as a result, it becomes applicable to a very wide variety of problems. And so in particular, this will be really good if we need to find eigenmodes or high quality factor resonant modes at just a single frequency. And what's nice is that we can actually treat layers with a very large difference in their length scales at this point, because each layer is assumed to be uniform. And so then the time that it takes to provide those solutions is really mainly dependent on just solving kind of like the 2D slice of that problem. And so if we have a limited number of layers, then that's actually going to dominate the overall time of the solution. And then changing the length is as easy as going back and then just changing one of the intermediate matrix elements and then composing them all together again. So it actually becomes pretty computationally tractable on even a single core machine. Obviously, multi-core processors are great, but not necessary. Now, I don't want to claim that this will solve every single problem necessarily. So this is going to have problems, of course, if we have a structure that's very hard to represent as like a small number of layers. If we have to basically represent it as thousands of layers, that's going to be very time consuming. And then the second point is that actually, if we have a very large absolute magnitude for the Fourier components, then it's going to slow down our convergence quite significantly. And that especially could be the case if we have a metal structure. So for plasmonics, it can be more challenging to converge to the correct answer, although it can be done. And we have a paper out recently from this year that shows that. And then there's another problem, which is just that the scaling is not necessarily of order n if you consider n to be the number of Fourier components, but actually oftentimes gets more like n cubed. And the reason for that is because solving this linear algebra problem usually requires a matrix inversion. And matrix inversions are expensive of order n cubed, where n is kind of the characteristic size of that matrix. So, of course, the other catch is that if you want to do different frequencies, you always have to recalculate at each frequency in order to get like the overall spectral response. So if you wanted to do very, very broad spectral range, this may not be ideal. But an alternative that may be better actually is time domain. And we will be covering that technique later in the class. Okay, so don't feel like you're missing out yet. But certainly for like structures that can easily be represented as a small number of layers and have like a relatively narrow bandwidth that you're concerned with, this can be a very nice technique. So just wanted to go into a little more depth on how do we like kind of set up our solution. So we already talked about this part where basically we wrote the eigenvalue equation as h q squared plus k plus script k times phi equals omega squared phi. And now we actually may want to multiply on the left-hand side by omega squared minus script k. And so the reason we do that is actually that creates like a much more symmetric problem for us to solve. And also like the reason why it works out well is partially because of the orthonormality condition that we're enforcing. Okay. And so at the end of the day, then we can solve this either as like an asymmetric problem that's maybe a little faster to set up, or a symmetric problem, but then there are kind of more elegant solutions for how to solve this generalized eigenvalue equation. So in other words, what we've done is we've taken it from something that looks like a phi equals omega squared phi to something that looks more like a phi equals b phi, where b is kind of a auxiliary matrix. Okay, and there are kind of standardized techniques that can help you solve each type of problem, but we found that the latter is probably more numerically stable and accurate in general. So in any case, once you have that set up, then you can also write everything like for the H fields in real space in kind of this mixed representation where you have like basically these Q values for the propagation in the Z direction. And these Q values can be kind of thought of as kind of like specific like propagation vectors like in both directions, in plus or minus directions. And we can construct an overall like parallel H field as kind of a sum of like these Hx and Hy values. And then we can also, of course, construct the E fields using Maxwell's equations and rewrite like all the Ex and Ey fields as well as the overall E parallel field in terms of very similar quantities as we calculated earlier. Of course, we pick up some minus signs from the opposite Z dependence and the exponential for the AN and BN terms in the H field. And so then we go from something that has like a plus sign for the H fields to something that has a minus sign here. And so of course the E and H fields have different spatial dependence in the Z direction perpendicular to the interface direction. And so now you can see that once we have defined these AN and BN, or now we call them AL and BL, between layers L and L plus 1, then we can actually define an interface matrix in this new notation. And so then this gives us something that looks like very similar to kind of the other S interface matrix, but it has like these auxiliary FL and FL+1 terms. And so then that just makes it a little easier to formulate this correctly. And now, in particular, what you'll notice is that these interface layers I, L, and L+1 could be written as kind of a composition of two matrix elements, which are ML inverse and then ML+1. So then this is actually where it becomes a little expensive computationally, because when you have to invert this matrix, of course, that is a little time consuming. So, I mean, there are some tricks, of course, to kind of speed up this evaluation, but you can't totally get away from it. So at the end of the day, you can kind of expand these ML and ML+1 terms based on kind of our earlier formulation. And then that gives you terms that are dependent on both the QL and the phi L expressions that we had like from earlier on in our setup. And so then ultimately, in order to get the final answer from the S-Matrices, then what we're doing is we're composing the interface layer matrices with the FL auxiliary terms and the previous expressions that we found for the S matrix before we expanded to the L+1 layer. Okay, and so then this is actually very similar to like what we talked about earlier of how do you like kind of systematically expand S matrices up to kind of the P+1 layer, except now we call it an L+1 layer. Okay, so obviously no technique is going to be better than the results that it can produce. And so this is just showing what happens when you have a relatively simple simulation in which you start off with just a uniform layer of error, and then you add in a couple layers that are periodic in the X direction. I think this is a 3D simulation. And so you can see that from kind of the side view, which is figure A in the Whitaker and Colshaw paper, then you see like there's kind of this notch that's etched into here, and you have layer 1 basically here in the top, layer 2 here, layer 3 is the slot in different refractive index, and then you have a uniform layer here and then another uniform layer here. So it's effectively a total of about 5 layers. And then looking at it from above, you can see that it actually creates a triangular lattice of air holes. And so you can actually use analytical expressions, specifically Bessel functions, to perform like the Fourier transform of these epsilons, which can then be used to more rapidly obtain the interface layer matrices and auxiliary terms, the FL, FL+1, and then construct the S matrix of the overall system. And so the result is actually shown on the right-hand side. So what you see essentially is that as you start adding more of these different Fourier modes, then you get just slightly different results, but it's mostly converged actually even like in the 3x3 case. So what that really tells you is that like for the range of photon energies that are being explored in this simulation, it's pretty much dominated by diffraction into the closest Fourier modes. And the other Fourier modes only play a minor role, and also kind of illustrates the idea that using an analytical approach to find the Fourier transforms oftentimes yields pretty good results. So I think in the next lecture, we're actually going to not only kind of go through a little more detail of what S matrices can really do, but also talk about some tools that are going to be available for you to use on nanoHUB to do S matrix calculations. Thank you.